Hello everyone, welcome to another lecture of the course Digital Signal Processing. So basically we are looking at the transformation of h of s to h of z. That is, the main aim is to have a conversion from analog filter to its equivalent digital IIR, that is infinite impulse response filter. And in the previous lecture, we saw an obvious substitution as S equal to 1 minus Z inverse. And in this substitution, what we saw that because of this, we are unable to get a proper mapping of omega to small omega. That is, proper frequency mapping is not observed. So basically the range of this frequency, that is capital omega, is from minus infinity to infinity. So this frequency was restricted to a range of minus 1 to 1, and because of this proper frequency mapping was not observed. The second thing that we saw, that the sigma equal to 0 line in the Laplace plane, so this is of the Laplace plane, was not mapped to unit circle. So this unit circle, that is r equal to 1, so this unit circle is basically in the z plane. And the condition of sigma equal to 0 is basically for the existence of Fourier transform for the continuous time signals or systems, and r equal to 1 is the condition for existence of Fourier transform in the z domain, or rather discrete time signals and systems. So we saw that this substitution, that is S equal to 1 minus Z inverse, was not a proper substitution, and therefore there is a need to devise or derive a proper substitution. So let us start from a simple example which we had already seen in the module 4 lecture 2. So we saw this simple RC circuit, and we had seen that its transfer function, that is y of s divided by x of s, was equal to 1 by RC divided by S plus 1 by RC. So this is basically the H of S, that is impulse response Laplace transform, and this y of s is basically the Laplace transform of the output, that is y of t, and this x of s is basically the Laplace transform of the input, that is x of t. And we also said that this RC circuit is basically a first order low pass filter. So this is first order low pass filter. So in general, we can write this first order low pass filter something like this, that is H of S is equal to B divided by S plus A. So we can write it something like this. So this would be equal to y of s divided by x of s. So what we have is y of s into s plus a is equal to b into x of s. So this is s into y of s plus a into y of s is equal to b into x of s. So what we have is y of s, rather s into y of s plus a into y of s is equal to b into x of s. Now let us take the inverse Laplace transform. So taking inverse Laplace transform, what we have is the inverse Laplace for this s into y of s is basically the differentiation of y of t with respect to t, that is y dash of t, plus a into y of t, which is equal to b into x of t. So what we have is y dash of t plus a into y of t is equal to b into x of t. So let us mark this as our first equation. Now using the trapezoidal approximation, that is using trapezoidal approximation, so this trapezoidal approximation is given as, say we have a function f of t which is equal to, say, t naught to t, or rather let it be equal to a to b f of t dt, or rather f dash of t dt. So let us write this as some integral I. So its approximate value is basically given as y dash of b plus y dash of a divided by 2 multiplied by b minus a. So we are going to use this trapezoidal approximation in order to represent this y of t. So we know that this y of t can be written as integration from t naught to t y dash of tau d tau plus y of t naught. So this t naught is basically the initial condition. So this t naught is initial condition, and using this trapezoidal approximation for this integral, we can write it as y dash of t minus y dash of t naught, plus y dash of t naught divided by 2 multiplied by t minus t naught plus y of t naught. So what we have is y of t is equal to y dash of t plus y dash of t naught upon 2 into t minus t naught plus y of t naught. So now we need to transform this system to a discrete time system. So a continuous time system is to be transformed to discrete time system, and the basic thing that we can do is to sample the signals. So let us sample, or rather sampling y of t and x of t with sampling duration t. So basically what we are going to do is we are going to replace this t by n into capital T, and this t naught be replaced by n t minus t. So what we get is y of nt is equal to y dash of nt plus y dash of nt minus t divided by 2 into nt minus t plus y of nt minus t. So this term gets cancelled. So what we are left with is t by 2 inside the bracket y dash of nt plus y dash of nt minus t plus y of nt minus t. So what we have is y of nt is equal to t into y dash of nt plus y dash of nt minus t whole divided by 2 plus y of nt minus t. Now if we look at this expression, so what we have is y dash of t plus a into y of t equal to b into x of t. So let's write it here. So equation 1 implies that y dash of t plus a into y of t is equal to b into x of t. So this can be written as y dash of nt plus a into y of nt is equal to b into x of nt. As we have sampled these signals, so what we have is y dash of nt is equal to b into x of nt minus a into y of nt. So let us substitute this in this expression. So what we have is y of nt is equal to t by 2 inside the bracket it is b x of nt minus a into y of nt plus it's b into x of nt minus t minus a into y of nt minus t plus y of nt minus t. So what we have is y of nt is equal to b into x of nt minus a into y of nt plus b into x of nt minus t minus a into y of nt minus t into t by 2 plus y of nt minus t. So what we are going to do is we are going to take common or take the terms corresponding to this y to the left hand side. So what we are going to do is we are going to group these terms that contain this y and take it to the left hand side. So what we have is y of nt inside the bracket 1 plus at by 2 plus y of nt minus t inside the bracket it is at by 2 minus 1, and similarly on the right hand side we are left with the x terms, that is bt by 2, and inside the bracket it is x of nt plus x of nt minus t. So now if we look carefully, we are left with a discrete time signals, that is this y of nt and this x of nt are basically y of n and x of n, as we have sampled them with the sampling duration of t. So we can take the Z transform of this expression. So what we will do is we are going to take Z transform So what we are left with is y of z into 1 plus at by 2 plus, now this is basically y of n minus 1, that is this y of n minus 1 t is basically y of n minus 1. So therefore its z transform would be equal to z inverse into y of z. So this would be equal to z inverse into y of z. Inside the bracket it is at by 2 minus 1, which is equal to bt by 2. Inside the bracket it is x of z plus z inverse into x of z. So what we have is y of z into 1 plus at by 2 plus y of z into z inverse into at by 2 minus 1 plus bt by 2 x of z into 1 plus z inverse. So let us take y of z common. So what we have is 1 plus at by 2 plus at by 2 into z inverse minus z inverse, which is equal to bt by 2 into x of z into 1 plus z inverse. So this can be written as y of z inside the bracket 1 minus z inverse, plus we can take this at by 2 common, so what we have is at by 2 inside the bracket 1 plus z inverse, which is equal to bt by 2 into x of z into 1 plus z inverse. So what we have is y of z upon x of z is equal to bt by 2 into 1 plus z inverse divided by 1 minus z inverse plus at by 2 into 1 plus z inverse, and this is basically the value of h of z. So what we have is h of z is equal to bt by 2 into 1 plus z inverse divided by 1 minus z inverse plus at by 2 into 1 plus z inverse. So now let us divide numerator and denominator by t by 2 into 1 plus z inverse. So what we have is h of z is equal to, in the numerator now we are just left with b divided by 1 minus z inverse divided by t by 2 into 1 plus z inverse, and here we are left with a. So what we have is b upon 2 by t into 1 minus z inverse upon 1 plus z inverse plus a. So what we have is h of z is equal to b divided by 2 by t into 1 minus z inverse upon 1 plus z inverse plus a. Now if we go back to our initial stage, that is this transfer function, we observe that this h of s, that is the initial condition that we had considered in the analog domain, so it was basically b upon s plus a. So initially h of s was considered as b upon s plus a, and our main aim was to convert this h of s, or rather map this h of s to its equivalent h of z, and if we compare these two expressions we can observe that, so if we compare these two expressions we can observe that this term, that is 2 by t into 1 minus z inverse upon 1 plus z inverse, is basically equal to s. So the equivalence that we obtain is this s is basically 2 by t into 1 minus z inverse upon 1 plus z inverse. So the expression that we have here, or the mapping that we have here, is basically s is equal to 2 by t into 1 minus z inverse upon 1 plus z inverse, and this transformation is referred as bilinear transform. So we started with this analog domain expression for a low pass filter, and then doing the trapezoidal approximation, then taking Z transform, we obtained the equivalent h of z expression and then found the equivalence between this s and this z. So the equivalence that we obtain is basically s equal to 2 by t into 1 minus z inverse upon 1 plus z inverse, and this is the expression for the bilinear transform. So in this lecture we found a transform or a method or a formula that allows us a transformation from h of s to h of z, which is known as the bilinear transform, and it is given as s equal to 2 by t into 1 minus z inverse upon 1 plus z inverse. So in the subsequent lecture, we are going to look at the insights of this bilinear transform and look at some of the properties or the benefits that this transform provides us. Till then, let's stop here. Thank you.